Welcome to the web seminar on B10 failure data in SIF verification. High demand only. During this web seminar, we are going to specifically address the use of B10 type failure data and its appropriateness. I'd just like to remind everyone that audio is provided via the internet, so please enable your speakers and mute your microphones. There is a question and answer tab at the top of the screen. Please use this mechanism to type in any questions you may have at any time. Questions will be read and answered. You may also use the one-on-one chat, which causes a pop-up window to appear on my screen. Again, welcome to everyone. I'm glad you're here. My name is Bill Goebel. I've been involved in functional safety for about 25 years now, and I've spent a lot of time in the world of reliability engineering and failure rate analysis. I work for a company called Exida. We are a group of people that come from diverse backgrounds, including development engineering, people who work for manufacturers, people who work for certification companies, and people who've worked in the field primarily in petrochemical. Exida does a lot of different things, but in the end, all of our work is focused on functional safety and cybersecurity. We do systems level consulting, safety lifecycle consulting. We do a lot of product certification. As an accredited certification body, we've done more certifications for 61508 than any company in the world. We do a lot of training, including, of course, this web seminar. We have a set of engineering tools, and we publish reference materials, and Exida operates the CFSE program for personnel certification. Our engineering tools range from alarm management through field failure data collection tools. All of the tools are meant to help implement the safety life cycle cost effectively. I'm proud to say that Exida has written, authored or co-authored virtually every single book written on functional safety published in the industry. We've authored many data books. We have a comprehensive set of books available on the Exida website, and they're available from isa.org or amazon.com. Now, we've talked many times before about the safety life cycle. You understand that as one of the fundamental concepts in our functional safety standards, the safety life cycle is a series of steps to be taken to minimize design mistakes and thereby increase safety and optimize cost. I didn't mean for you to read all the boxes, but I wanted you to see that all the boxes in the Exida model of the safety life cycle define a process. The process meets all the requirements of 61508, or in this case, it's oriented towards 61511. In the realization phase of the safety life cycle, the performance-based concepts appear. Now, you may recall that as another one of the fundamental concepts in 61508 and 61511, performance calculations are done during a conceptual design phase to verify that any given design meets safety integrity requirements. There are no prescriptive rules about any particular design that must be used for any particular sill level. Engineers are free to create their own designs and to optimize cost. But in order to do this calculations, failure rate data must be available. Failure rate and failure mode data must be available for every part in the safety instrumented function. How do you get this failure rate data? I will readily admit there was a time back in 1996 when the first ISA SP84 standard was released, introducing the performance-based functional safety concept. The whole idea of doing calculations was kind of tough back then because failure rate data was a bit hard to come by. I remember a lot of debate about using the performance-based concepts and getting failure rate data, and there's even some of that debate today, but I can guarantee you we're in a very different environment today than we were a decade or so ago. Today I can get good data from third-party FMEDA reports. The advantage of this is that it's very detailed and very complete, but of course one FMEDA may not be the same as the other because the FMEDAs depend on a good component failure rate database. One can get failure rate data from end-user field failure studies. The problems with these are that in the many failure rate studies that I have done at Exeter, I've found tremendous variations in the amount of data collected. I have found very different definitions of what is a failure. What one person would call a failure, another person would call an abuse, not a failure. Well, if something fails, it's a failure. There's great amount of categorizing and merging of different technologies, and fault isolation is often not completed, and therefore people will have failure records for multiple components when in fact only one has failed. There are problems with manufacturers' field failures. Of course, the MTBF studies done by a particular manufacturer may very well be quite self-serving. Now, the plus is that it's real data, but the calculations methods vary widely. And you must ask, how can a manufacturer know what percentage of actual failures are returned? Manufacturers base these calculations on failure reports when people return failed product back to the manufacturer. At Exeter, we have done a study on what percentage of failed products get sent back to the manufacturer. And depending on product type, that number and application, that number varied between 0 and 40%. What if the average were more like 10%? The real number of failures in the field might be 10 times higher than the manufacturer reports. So, those kind of failure studies, especially those done by the manufacturers themselves, may give us some very different failure rate data and very optimistic failure rate data. In the last couple years, I have seen data based on cycle testing. This data is what I call B10 data. The concept is that a cycle test is operated on a particular set of products, and this is, of course, useful for mechanical or electromechanical components. And based on those test results, failure rates are calculated. All these methods have pluses and minuses and certain levels of applicability. We'll talk about each one, and then we'll focus our conversation on the B10. FMEDAs are predictive failure rate, failure mode models that can be constructed based on a component database. The accuracy of an FMEDA can be very good, but the component database has to be nicely calibrated for the particular application and the particular environment. At Exeter, we do a lot of FMEDA analysis. Our component database is calibrated for low-demand process industry type applications. We've calibrated the component database based on hundreds of field failure studies, primarily from petrochemical and power, some nuclear, and we update the component database virtually 100 times over the last 12 years, and we found that the current FMEDA failure rates match product failure rates from the field in the process industries, in low-demand applications, very nicely. However, FMEDA predicts a product failure rate, not what I call site-specific failure rates. In other words, maintenance-induced failures, and we'll talk a little bit about that later. Now, if you're fortunate enough to work for a company that collects good field failure data at a petrochemical or chemical company, you can use that as a source of data. Now, the plus, of course, is that it's real failure rate data, but the minus is, as I said before, there are people who have very different definitions of what's a failure. In order to find out the quality of any particular data set, here at Exeter, we always ask, when is a failure report written? And sometimes it's written. For example, in one case, a failure report was written only when a product was sent out for repair. They didn't even count it as a failure if they could fix it in-house. That was not good. What is the definition of failure? Are as-found conditions recorded during a proof test, and what were the operating conditions? It's very important to understand all this when evaluating field failure calculations done in the field. And the reason, there are wide variations in how people interpret and define failures. But that's okay. There's still a lot of useful data there. And even, although I criticize manufacturers' warranty data studies, there is real data there, and in fact, manufacturers can provide some useful information. When the report is done by a manufacturer, I've often found that these are quite self-serving, and therefore the failure rate data is optimistic because many returned items are marked "no problem found." In other words, the incoming test procedure may not be good enough. I've seen calculations on operational hours based on shipping records, and it is assumed that all failures were returned. And that's terribly optimistic and results in relatively low failure rate numbers, which are not good for safety verification, because they might lead us to put in not nearly enough safety into our designs. Recently, I've seen some failure rate data, which I call the B10d failure data. Now, the B10d is oriented for mechanical and electromechanical components. The B10 method uses cycle testing. A cycle testing is done on a set of products. Cycle test. In other words, imagine a rack of relays. Let's say there's 20 of them. And we wire all the coils up to a power supply. And we turn them on and off with an oscillator, operating them pretty much as fast as we can go, because these kind of tests typically involve a lot of cycles and may take weeks, if not months. and we need to get some test results. Besides that, it burns up a lot of power and it's noisy. If the laboratory where these tests are run is near your office, you would understand my comment. Anyway, the test is run until 10% of the units fail. If 20 units were on test, for example, as soon as the second one fails, you stop the test. You count, or you obviously have some kind of a cycle counter, which counts the number of cycles until the 10% failure report, and that's called the B10 point. So we have a number. It's a number in terms of cycles. What do I do with that? We convert the number of cycles into a time period by knowing the number of cycles per hour in any particular application. For example, imagine if we ran 100,000 cycles, and there was, in a particular application, there was 1 cycle per hour. Well, we could just scale. We would know, therefore, that the B10 point would be 100,000 hours. That's a time interval. Now, a failure rate is calculated by saying we know that 10% of them fail at the 100,000 hour mark. And we assume, or the method assumes, that there is a constant failure rate up until the 100,000 hour point. The 100,000 hour point is called the end of useful life. The failure rate during the useful life is calculated simply by number of failures divided by the 100,000 hours. The total failure rate is divided into safe versus dangerous by simply assuming 50% are safe, 50% are dangerous. And then many calculate a metric called MTTFD by taking the inverse of the lambda D failure rate. So, beginning to get a picture of what this method is, it's a test. It's a laboratory test based on cycling or movement. Now, what is often not stated is the assumptions. The assumptions as to when that particular test and therefore the particular results are valid. Data is typically presented in terms of an MTTFD, which is in years, or a B10 point in cycles. This is a particular chart from ISO 13849-1, 2006. It is a functional safety standard for the machine safety industry. And this kind of makes sense for machine safety. It really does. Because imagine a stamping machine or a press, and that machine is running ka-whump, ka-whump, ka-whump. Then it might be running a stamp every 10, 15 seconds. 4 cycles per minute. What's that? 240 cycles per hour. This machine could be moving pretty fast. The limiting factor is mechanical or electromechanical wear out. And so the whole concept behind the cycle testing is simple. It assumes the constant failure rate during the useful life is due to premature wear out. It assumes that all other failure modes are totally insignificant compared to the failure rate of premature wear out. And premature wear out just means any parts that fail sooner than they should because of a manufacturing defect or a materials defect or something along those lines. So remember, the assumption is that all failures are due to premature wear out, and that all other failure modes are so small they are totally insignificant. Now, it's a fact that a lot of research shows that other failure modes become very significant when products aren't being rapidly cycled. Sometimes these failure rates become significant if a product is static or does not move, even within 24 hours. New failure modes manifest themselves. It's just absolutely a fact of life. Consider a relay. Many relay manufacturers who focus their efforts toward the machine safety world publish B10d data or MTTFD data for their relays. This is very appropriate if your application is constantly cycling. But what happens if your application is not constantly cycling? Well, relays used in de-energized to trip applications will have much higher coil temperatures when energy is applied, basically 99 or 100% of the time, as compared to 50% of the time. Think about it. One of the major failure modes of a relay in a de-energized to trip application is coil burnout. You'll never see a coil burnout at a 50% duty cycle. The internal coil temperature is nonlinear related to power. Very different failure rates in static applications. Relays will absolutely suffer failures due to stiction in all moving joints, depending on the complexity of the design and potential bearings and so forth. Most designs are simple metal on metal or a flexible member. It's possible in some designs that there will be stiction and that the spring that returns a relay into position when it's de-energized will lose force. The bottom line is failure rates will be much higher in static applications where a relay stays energized and static for long periods, especially if it's energized and static for periods of time like 1 year. Like 1 year. What kind of applications are those? It's mainly the process industries, where you don't expect dangerous conditions very often, and therefore, if with a 1-year proof test cycle, the only time the relay that moves is when you do a proof test. Think about that. It's even worse with solenoids and actuators and products that have seals. When O-rings or other seals are part of a product, many failure modes become very significant when a product remains static for basically 100, 200 hours, 1 week. Stiction, cold welding, corrosion binding. In a normal de-energized to trip process industry application, most of these failures would prevent the product from performing the trip function and would be classified as dangerous. None of these would ever appear in a cycle test failure, in a cycle test. None of these failures. So again, what we have is a failure rate that would be much higher in low-demand applications. Now, that doesn't mean that the certificates and the various certification bodies are trying to mislead you, but everyone involved in safety should know and understand when an assessment was done based on high demand versus low demand failures. Many certifications on mechanical and electromechanical products are based on cycle testing or other mechanisms that assume frequent movement. All the reports I've read do not try to hide this fact. It's right there in the report. Take a look if you can read that line that's highlighted in a red box. It says, assumed demands per year. 10. So this analyst assumed that it would be moving at least 10 times per year. It could be moving much more than that. Now, my research shows that, in fact, to utilize cycle test data, you really have to have at least 50 to 100 demands per year. But so I would not go as low as 10. Our research shows you need more like 50 to 100. And that has a big difference when you scale the failure rate, as you might imagine, having the failure rate method described to you. But the bottom line is, don't just assume when there's a 61508 certified product that the failure rates given are useful and valid in low demand applications. Just checking. I haven't seen anybody put up any questions yet. Do not hesitate to do so. How different are these different methods and these different numbers? I put together a chart comparing failure rate data published for a solenoid valve. I picked 2 data points based on FMEDA. You can see these numbers are 1.59 e to the minus 7 to 5.66, depending on the complexity and the size of the solenoid valve. Generally speaking, spool-type solenoid valves have a lot more O-rings and seals, and therefore you'll find they have a higher low-demand failure rate. The FMEDA numbers are frequently compared to actual field failure studies like this one from Dow Chemical that has a number 3.51, which actually is right in the middle of the FMEDA range, probably showing that they have averaged a number of different types of solenoid technologies into one number, because only one number was published. They probably don't distinguish the difference between a spool type and a pilot operated and so forth. The ARETA data for a solenoid valve is the highest number. It shows 9 times 10 to the minus 7, so the ARETA is not quite twice as much as the upper end FMEDA data. And I have to admit I was very curious as to why that was. And I did travel up to Norway and have a meeting with the people who analyzed the ARETA data. And it became very clear that ARETA includes what I call site-specific data in their reports, whereas FMEDAs are very oriented or include only failures due to the product. Now, what does that mean? If you have very relatively low safety culture, if you have relatively poor maintenance capability, and a lot of failures are actually caused by mistakes made by your maintenance and operations people, then those kind of failures would not be included in an FMEDA. Now, I do happen to think it's important that we model those. And so at Exeter, we have a maintenance capability model that treats those very separately. In any case, we see a set of numbers that vary roughly between 1.5 and 9 times e to the minus 7, all roughly within one order of magnitude. Cycle test results provide much lower numbers. In one set of cycle test results, 8, or let's say 9 times 10 to the minus 9 was published. And that's quite a bit lower than even the lowest FMEDA number, and literally, boy, it looks like 2 orders of magnitude lower than ARETA. Now that's totally valid for a high demand rapidly moving application, but if you mistakenly use such a number in a low demand application, you could be making a very dangerous error. Another cycle test result is 4.53 times e to the minus 10. That dangerous failure rate is less than the accepted failure rate of a quarter-watt resistor. I think that one was misscaled, actually. I think they didn't use enough cycles per hour. I have another piece of solenoid valve failure rate data that I got. It's from a manufacturer's warranty study, and it's pretty optimistic, but not nearly as optimistic as cycle test data. So the bottom line is, B10 data is not suitable for low demand applications where the products aren't moving. Failure rates due to cold welding, stiction, corrosion, coil burnout become very significant if a product sits in a static application, even for 24 hours, and certainly become significant if a product isn't cycled at least once a week. Now, there are such applications in the process industries. I've seen one or two, but for the most part, cycling isn't done until there's a demand or a proof test. So you might find a product sitting around for years. These low failure rate data, these low failure rates would lead people to conclude they don't need to do proof testing. It would lead people to conclude they don't need redundancy. In other words, it's dangerous. Safety is serious business. Competency is required. And that's what we're trying to do in these seminars, to make sure you understand that failure rate data must match the application. Does anybody have any questions or comments? There's something. Oh, that's good. Thanks. Hold on. Let me read this out loud. I work in operations, and I'm more interested in field failure rate measurement. The problem that I have is over a few years of the life of equipment, the dangerous undetected failure rate is very difficult to obtain. Yeah, I agree. On the other hand, safe and detected are much higher, yes, and we get some numbers. I use the safe failure fraction to get a calculated dangerous undetected failure rate to validate the PFD calculation. Is this the right way of doing that? Well, first of all, we definitely have an entire set of 2 or 3 web seminars coming up in January on field failure data collection and analysis. And so I wanted to tell you that we're going to be spending some time focused on this particular subject in January or February. Secondly, your method may be valid if your safe failure fraction is valid, but of course any number that you have provides a basis of comparison and gives you some idea what the DU failure rate might be, as opposed to no idea. I personally recommend the use of FMEDAs as comparison models. And if you get your safe failure fraction from an FMEDA, and if you have good failure rate data collection, the method you're proposing seems very reasonable. Good luck. And please come back for these, stay tuned for these additional web seminars on field data collection and analysis. One of my favorite topics. Any other questions? Okay, another one's coming in. Are cycle test results ever valid? Okay, fair question. And the answer is yes, they're absolutely valid when a product is being cycled frequently. I had a job last week where it kind of was a packaging line, and there was a set of equipment that was moving and relays that were cycling once a week, solenoid valves that would cycle once a week. And in that application, I was auditing SIF verification calculations done by an engineering company, and I concluded the numbers they used were indeed valid, that cycle test data could be used in that application, and it was good for them because they had a much lower, in this case, PFH, because they had it was a high demand application. High demand application numbers are valid. Go ahead, use these numbers. The certification bodies who publish these numbers are not deliberately trying to mislead you, but I have come across a lot of people who don't take the time to understand what the reports say. I will say right now, FMEDA data from Exida is all calibrated toward low demand. Occasionally we will do cycle testing and publish a high demand number, but most manufacturers that we work with are focused in the process industries. Okay, any other questions? I'd very much like any you have. Happy to answer them as best I can. Well, I don't see anything else right now, so let me just say that if you have any questions, please do not hesitate to send me an email. I'll type my email address. If you think of some question tomorrow, send it to me and I'll get back to you with an answer, asynchronously. That's what I like about email. Just wait another moment. Make sure there are any other questions or comments. All right, well, I thank you all very much for attending the Exida web seminar. Hopefully you'll find your time well spent, your competency improving. And remember, there's some questions just like this on the CFSE exam. So when you attend the Exida web seminars, you're getting some very good free CFSE training. I'll check one more. Thanks. If we use the same motor contactor for motor control and interlocking so that it is cycled, say once a day, would it be acceptable to use the following formula to calculate MTFD? Well, to B10.1, that looks like once a day, 360 days a year. I don't see any problem with that. Make sure you keep your units correct. But that's an excellent example of a product that is being cycled, and therefore the B10d points are probably going to give you relatively accurate failure rate data. Thank you for commenting, Daniel. If I were auditing your work, I would probably judge that to be perfectly acceptable. Thanks for asking. All right. I don't see any others for right now, so let me again thank you for attending the Exida web seminar. Stay tuned. Look for white papers on the Exida website, all free of charge. Thank you very much for attending, and stay tuned for more web seminars. Goodbye.